previous class we have seen effect of standardization and how to find out different distances like Manhattan distance, Euclidean distance and Minkowski distance. Then I have explained how to select the variables. In this lecture we are going to see when you are collecting the data, if you are missing some data is not available, how to handle that situation. Then very important concept of similarity and dissimilarity matrix. That is our agenda for this lecture. First let us see how to handle the missing data. It is often happens that not all measurement are actually available. So there are some holes in the data matrix, that is a missing value in the data matrix. Such an absent measurement is called missing value. It may have several causes. The value of measurement may have been lost or it may not have been recorded at all by oversight or lack of time. Sometimes the information is simply not available. For example, birth date of a foundling, or the patients may not remember whether he or she ever had the measles, or it may be impossible to measure the desired quantity due to the malfunctioning of some instrument. In certain instances the question does not apply, or there may be more than one possible answer when the experiments obtain very different results. So how can we handle a data set with the missing values? That is the important question now. In a matrix we indicate that the absent measurement by means of some code. If there exists an object in the data set for which all measurements are missing, there is really no information on this object, so it has to be deleted. Analogously, a variable consisting exclusively of missing values has to be removed too. If the data are standardized, the mean value m of the fth variable is calculated by making use of present values only. The same goes for your mean absolute deviation. So mean absolute deviation, that is SF equal to 1 by n modulus of x1f minus mf and so on plus xnf minus mf. In the denominator we must replace n by the number of non-missing values for that variables, but of course only when the corresponding xi is not missing itself. In the computation of distances based on the either xi or the zi, the similar precautions must be taken. When calculating the distances d of I comma j, only those variables are considered in the sum of which the measurements of both objects are present. Subsequently, the sum is multiplied by p and divided by the actual number of terms. In the case of Euclidean distances, this is done before taking the square root. Such a procedure only makes sense when the variables are thought of as having the same weight. For instance, this can be done after standardization. When computing these distances, one might come across a pair of objects that do not have any common measured variables. So their distance cannot be computed by means of above mentioned approach. Several remedies are possible. One could remove either object or one could fill some average distance value based on the rest of the data, or by replacing all missing xif by the mean of mf, that variable, then all distances can be computed. Applying any of these methods, one finally possesses a full set of distances. Then we will go to the another topic, that is dissimilarities. The entries of n by n matrix may be Euclidean or Manhattan distances. However, there are many other possibilities, so we no longer speak of distances but dissimilarities or dissimilarity coefficients. Basically, dissimilarities are non-negative number, that is d of I comma j, that are small close to 0 when I and j are near to each other, and they become large when I and j are very different. We shall usually assume that dissimilarities are symmetric and that the dissimilarity of an object to itself is 0. But in general, the triangle inequality does not hold. Dissimilarities can be obtained in several ways. Often they can be computed from variables that are binary, nominal, ordinal, interval or combination of these. Also, dissimilarities can be simple subjective rating of how much certain objects differ from each other from the point of view of one or more observers. This kind of data is typical in the social science or in the marketing. Let us take one example, then I will explain the concept of dissimilarities. 14 postgraduate economics students coming from different parts of the world were asked to indicate the subjective dissimilarities between 11 scientific disciplines. All of them had to fill in a matrix like in table 4 in the next slides, where the dissimilarities had to be given as integer numbers on a scale of 0 to 10, where the 0 represents identical, 10 represents very different. The actual entries of the table in the next slides are the average of these values given by the students. It appears that the smallest dissimilarity is perceived between mathematics and computer science. That value is 1.43. Mathematics and computer science. This is our smallest dissimilarity. Whereas the most remote fields were psychology and astronomy. Psychology, astronomy. So, this table represents dissimilarity matrix. From that, we can directly read which is having lesser dissimilarity, which is having more dissimilarity. If one wants to perform a cluster analysis on a set of variables that have been observed in some population, there are other measure of dissimilarity. For instance, one can compute the parametric Pearson product moment between the variables f and g, or alternatively non-parametric Spearman correlation. Here the dissimilarity can be found with the help of your Pearson correlation or Spearman correlation. We know that the Pearson correlation is the parametric method, Spearman correlation is non-parametric method, because Spearman correlation is applicable only for ordinal data. Both the coefficients lie between -1 and +1. Which one I am saying? Where our Pearson and Spearman correlation, and do not depend on the choice of measurement units. We not bother about the units, because we are going to see the range of correlation coefficient is -1 to +1. Similarly, the Spearman correlation value also between -1 to +1. That value does not depending upon what type of units of the data. The main difference between is that the Pearson coefficients look for a linear relationship between variables f and g, whereas the Spearman coefficient searches for monotone relations. So, this is formula for our correlation coefficient. So, we call it as R, the correlation coefficient. We have studied this formula already. So, the correlation coefficient rho is this is nothing but covariance of x comma y divided by standard deviation of x, standard deviation of y. So, this is in some other format. This is x comma y, the correlation coefficient, not x comma y, here you can call it as f comma g. Correlation coefficients are useful for clustering purposes because they measures the extent to which two variables are related. Correlation coefficients, whether parametric or non-parametric, can be converted into dissimilarities d of f comma g, for instance by setting by this relationship. So, dissimilarity between object f comma g equal to 1 minus r, that is the correlation coefficient between f comma g divided by 2. With this formula, variables with a high positive correlation receive a dissimilarity coefficient close to 0, whereas the variables with a strongly negative correlation will be considered as very dissimilar. Why this kind of conversion is required? The range of dissimilarity is between 0 to 1, but sometime what will happen, the value of correlation coefficient between -1 to +1. So, convert into 0 to 1 scale, we can use this transformation. So, now we enter into another concept called similarities. Previously we are explaining about dissimilarity, now we are going to study about what is similarities. The more objects I and j are alike, so the larger will be similarity between S I comma j becomes. Such a similarity S of I comma j typically takes on values between 0 to 1, whereas 0 means that I and j are not similar at all and 1 reflects maximum similarity. Values between 0 and 1 indicate various degrees of resemblance. Often it is assumed that the following conditions hold. So, S1 0 less than or equal to S of I comma j less than or equal to 1, because the range of similarity is between 0 to 1. S2 the similarity between I comma I itself 1, the similarity S I comma j is equal to j comma I. We will continue the concept of similarities. For all objects I and j, the numbers S of I comma j can be arranged in an n by n matrix, which is then called similarity matrix. Both similarity and dissimilarity matrices are generally referred to as proximity matrices, sometimes as resemblance. In order to define similarities between variables, we can again resort to a Pearson or Spearman correlation coefficient. However, neither correlation measures can be used directly as a similarity coefficient because they also take on negative values. Because we cannot take the value of correlation and Spearman correlation as it is, because they may range between -1 to +1, but the similarity value is between 0 to 1. So, in that case we have to go for some transformation. Some transformation is in order to bring the coefficient into 0 to 1 range. There are essentially two ways to do this depending on the meaning of the data and the purpose of the application. If the variables with a strong negative correlation are considered to be very different because they are oriented in the opposite direction, like mileage and weight of a set of cars, then it is best to take something like this following. You have to follow this transformation, S of f comma g equal to 1 plus r of f comma g. What will happen here? We have added some constant, so that constant will nullify the negative effect, which yields the similarity between f and g equal to 0 whenever the correlation coefficient is -1, because -1 and +1 will become 0. So, this take care that the similarity value comes between 0 to 1. There are situations in which variables with a strong negative correlation should be grouped because they measure essentially the same thing. For instance, this happens if one wants to reduce the number of variables in a regression data set by selecting one variable from each cluster. In that case, it is better to use formula like this: similarity between f comma g equal to the modulus value of correlation coefficient between f and g, which yields that the similarity between f comma g equal to 1 when the correlation coefficient is -1. We have to take only the positive values. Suppose the data consists of similarity matrix, but one wants to apply a clustering algorithm designed for dissimilarities, then it is necessary to transform the similarities into dissimilarities. The larger the similarity, that similarity between S I comma j, between I and j, the smaller their dissimilarity d of I comma j should be. Therefore, we need a decreasing transformation. This is a very important result. So, what it says that if we want to know the dissimilarity between two objects I comma j, that is nothing but 1 minus similarity between I comma j. Let us take a binary type variable. For that, let us find the similarity and dissimilarity. Suppose a contingency table for binary variable is given. Here there is an object I and object j. You see that object I is 1 0, there are two possibility, object j also 1 0. So the q represents where the object I also takes value 1, object j also takes value 1. This R represents, q is the number of values. Here R represents I equal to 1, j equal to 0. This S represents number of values where I equal to 0, j equal to 1. T represents both I and j equal to 0. The row sum is q plus r for when I equal to 1. When I equal to 0, the row sum is s plus t. Same say the column sum is when j equal to 1, the column sum is q plus s. When j equal to 0, the column sum is r plus t. So the sum of QRST, that is nothing but your value p. What is the meaning of this QRST? Q represents the number of variables that equal 1 for both objects I and j. You see that Q is the number of variables. R is the number of variables that equal 1 for object I but that are 0 for object j. S represents number of variables that equal 0 for object I but equal 1 for object j. So T represents the number of variables that equal 0 for both objects I and j. The total number of variables is P, where P equal to Q plus R plus S plus T. The dissimilarity between symmetric binary variable. So from the previous table, what is the meaning of symmetric binary variable is, example is gender, suppose 0 male, 1 female. You can reverse the code also, there won't be any problem on this. So that is example of symmetric binary variable. So for symmetric binary variable, how to find out dissimilarity? So dissimilarity between I comma j is, it is r plus s. What is r plus s? We will go this. So this one, the dissimilarity is this value r plus s divided by sum of all values, r plus s divided by q plus r plus s plus t. Then let us see what is the meaning of asymmetric binary variable. A binary variable is asymmetric if the outcomes of the states are not equally important, such as positive and negative outcome of a disease test. By convention, we shall code the most important outcome, which is usually the rarest one, by 1. For example, HI positive, that is the rarest one, we will code it as 1, and the other by 0, HIV negative. Given two asymmetric binary variable, the agreement of two ones, that is a positive match, is considered more significant than that of two zeros, that is a negative match. Therefore, such binary variable are often considered as monary, as if having only one state, because we need not bother about the 0 state, because 0 state is that non-presence of HIV, because we are more concerned about only presence of HIV, where the state of 1 is more important. Now let us see how to find out dissimilarity value between asymmetric binary variable. The same table which I have given, contingency table which I have given, previous table I have given. So the dissimilarity between asymmetric matrix is d of I comma j. So we are considered about only r and s. In this, in the denominator there won't be t, because we are not considering 0. So only we are writing q plus r plus s. If it is symmetric binary dissimilarity, the difference is there was a t element was there here, but here in the asymmetric binary dissimilarity formula there is no t element. Even we have seen this relationship, that relationship called Jaccard coefficient, that is the similarity between I comma j equal to 1 minus dissimilarity. So similarity q divided by I comma j, where is the q? This one, because we are bothered about only the presence of 1. So q divided by q plus r plus s, that is your similarity between I comma j for a asymmetric binary variable. So, if you want to know dissimilarity, that is simply the similarity equal to 1 minus dissimilarity between I and j. Now, let us take an example. We will find out for asymmetric binary variable how to find out dissimilarity matrix. This table shows there are different name is there, Jack, Mary, Jim, there is a gender. Here gender is symmetric binary variable, we are not going to consider this one, because this is a different test, fever, cough, test 1, test 2, test 3, test 4, this is asymmetric variable, because where the presence of 1 is more important. Here y represents and p represents 1, n represents 0. For this matrix, let us find the dissimilarity matrix between Jack and Mary. So, I brought the table again. Let us find out the dissimilarity matrix between Jack and Mary. So, for Mary there are two possibility 1 0, for Jack there is another two possibility 1 and 0. So, let us count how we got this 2. So, Mary also 1, Jack also 1, there are two possibilities there. Mary, this is one possibility, this is another possibility. So, there is a 2 count, so we written as 2. Then how we got this 1, Mary is 1, Jack is 0. So, that means this one, where Mary is 1, Jack is 0. Now, we will go to this column where Mary is 0, Jack is 1. So, Mary 0 is this one, I think there is no value for this. Let us see the last option, that is Mary also 0, Jack also 0. So, this 1, 2, this is 3, that is a 3. So, if you want to know the dissimilarity distance between Jack and Mary, so we know that the formula is, so we will add this one 0 plus 1 divided by 2 plus 0 plus 1. So, we got 0.33. Similarly, now let us find how to find out the dissimilarity between Jack and Jim. So, Jack is taken in rows, Jim is taken as in the column. So, first we will find out how we got this 1. So, this case is Jack also 1, Jim also 1. So, this is this category. So, Jack also 1, Jim also 1. I think there is only one possibility. So, it is 1. How we got this 1? The Jack is 1, Jim is 0. So, this value Jack is 1 presence, Jim is 0, that is 1. So, how we got this one, where the Jack is 0, Jim is 1. So, Jack is 0, yeah, this value Jack is 0, no means 0, y means 1. Let us see how we got this value 3. So, Jack also 0, Jim also 0. So, this one, no, not this one, this one 1, 2, 3, that is why we got the 3 values. So, if you want to know the dissimilarity between Jack and Jim, so this is 1 plus 1 divided by 1 plus 1 plus 1. So, 2 divided by 3, it is 0.67. Let us take another example, the dissimilarity between Jim and Mary. So, Mary, there is a 2 option 1 and 0, for Jim also there is a 2 option 1 and 0. Let us see how we got this value 1. Mary is 1, Jim also 1. So, this possibility, it is 1. The second case, Mary is 1, Jim is 0. Mary is 1, Jim is 0. This is one value. Mary is 1, Jim is 0. So, there are two possibilities. So, that is why we got the value 2. How we got this value 1? Mary is 0, Jim is 1. So, Mary is 0, Jim equal to 1, that is this value. So, how we got this 2? Mary also 0, Jim also 0. So, these two possibilities, Mary also 0, Jim also 0, case 1. Here also Mary is 0, Jim also 0. So, if you want to know asymmetric dissimilarity between Jim and Mary, it is 1 plus 2, this value plus this one divided by this 1 plus 2, that is 4. So, we got 0.75. So, this is the way to find out asymmetric dissimilarity between different variables. In this class, we have seen how to handle the missing data for cluster analysis. Then I have explained the concept of similarity and dissimilarity matrix. Then we have studied symmetric and asymmetric binary variable and how to find out the dissimilarity between symmetric binary variables and dissimilarity between asymmetric binary variables. Thank you.